Dear students, in this session I will discuss curves drawing. Curves drawing. Curves are trajectories of moving points. Curves are used as a function assigning a location of that moving point in two-dimensional or three-dimensional to a parameter, that is parametric curves. Curves are useful in geometric modeling and they should have a shape which has a clear and intuitive relation to the path of the sequence of control points. More often we use the curve that is developed by Bezier. Bezier curve was discovered by French engineer Pierre Bezier, which is popularly known as Bezier curve. Bezier curves are used in computer graphics to produce curves which appear reasonably smooth and only requires two endpoints and some other points to control the endpoint tangent vectors. Bezier curves are commonly found in pointing and drawing packages as well as CAD system. Since they are easy to implement and they are reasonably powerful in curve design. Two-dimensional curves generated from 3, 4 and 5 control points. On the screen you are seeing the Bezier curve, which is mathematically represented as summation of pi multiplied by bi to power n multiplied by t within the limit of I is equal to 0 to n, where pi is the set of points and bi to the power n multiplied t represents the Bunsen polynomials which are given by bin t is equal to ni multiplied by 1 minus t n minus 1 ti, where n is the polynomial edge, I is the index and t is the variable. The simplest Bezier curve is the straight line from the point P0 to P1. As you were seeing in the figure, there are three figures on the screen. The first one is of simple Bezier curve. The second, that is quadratic Bezier curve. The quadratic Bezier curve is determined by 3 points, 3 control points, whereas the cubic Bezier curves is determined by 4 control points. All these 3 are appearing on the screen. A spline curve. A spline is a flexible stripe used to produce a smooth curve through dilated set of points known as control points, which indicates the general shape of the curve. There are two types of spline curve. Number one is interpolation curve, which are commonly used to digitize drawings or to specify animation paths, while the another one, which is approximation curve, are primarily used to design tools to structure object surfaces. A spline curve is defined, modified and manipulated with operations on the control point. By interactively selecting spatial positions for the control point, a designer can set up an initial curve. After the polynomial fit is displayed for a given set of control points, the designer can then reposition some or all of the control points to restructure the shape of the curve. In addition to curve, this can be translated, rotated or scaled with transformation applied to the control points. Dear students, we have already learned, we have already discussed how an object can be translated, rotated or scaled in our previous session. CAD packages can also insert extra control points to aid a designer in adjusting the curve shapes. As per requirement, extra points may be added to the curve. B-spline curves. The Bezier curve produced by Bernstein basis function has limited flexibility. Flexibility like the number of specified polygons vertices fixes the order of the resulting polynomial which defines the curve. The second limiting characteristic is that the value of the blending function is non-zero for all parameter values over the entire curve. The B-spline basis contains the Bernstein basis as the special case. The B-spline basis is non-global. Following are the characteristics of B-spline curves. The sum of B-spline basis functions for any parameter value is 1. Each basis function is positive or 0 for all parameter values. Each basis function has precisely one maximum value except for k is equal to 1. The maximum order of the curve is equal to the number of vertices of defining polygon. The degree of B-spline polynomial is independent on the number of vertices of defining polygons. B-spline allows the local control over the curve surfaces because each vertices affects the shape of a curve only over a range of parameter values where its associated basis function is non-zero. The next characteristic is the curve exhibits the variation diminishing property. The curve generally follows the shape of defining polygons. Any affine transformation can be applied to the curve by applying it to the vertices of defining polygons. The curve line within the convex hull of its defining polygon. So, B-spline curves are more appropriate and useful in object preparation. The next is illumination model. The illumination model, which is also known as lightning model and sometimes referred to as shading model. We often used it to calculate the intensity of light that we should see at a given point on the surface of an object. Here, surface rendering, which means a procedure for applying a lightning model to obtain pixels intensities for all the projected surface positions in a scene. A surface rendering algorithm uses the intensity calculations from an illumination model to determine the light intensity for all projected pixels positions for the various surfaces in a scene. Surface rendering can be performed by applying the illumination model to every visible surface point. Lightning sources are referred as light emitting sources and reflecting surfaces are considered as walls of a room and termed light reflecting source. We often find that a luminous object in general can be both a light source and light reflector. The simplest model for a light emitter is a point source. When light incident on an opaque surface, part of it is reflected and part is absorbed. The amount of incident light reflected by a surface depends on the type of material. Shiny materials reflect more, of the incident light, and dull surfaces absorb more of the incident light. So, we have two types of reflections: surfaces that are rough or granular tend to scatter the reflected light in all directions, and the scattered light, which is called diffuse reflection. The another one, the highlighting effect, is a specular reflection, which is emit from light sources, create highlights or bright spots. The highlighting effect is more pronounced on shiny surfaces than a dull surface. Now, we will discuss one by one diffuse reflection. Diffuse reflection are constant over each surface in a scene. The fractional amount of the incident light that is diffusely reflected can be set for each surface with parameter Kd, d for deflection. The diffuse reflection coefficient or diffuse reflectively, parameter Kd is assigned a constant value in interval 0 to 1. To simulate a surface that absorbs most of the incident light, the reflectivity value becomes nearer to 0. If the surface is exposed only to ambient light, we can express the intensity of the diffuse reflection at any point on the surface as I am diff equal to Kd multiplied by Ka. Here the diffuse reflection from the surface are scattered with equal intensity in all direction, independent of viewing direction. The next one is specular reflection and Phong model. We see a highlight or bright spot at certain viewing directions. This phenomenon, called specular reflection, is the result of total or near total reflection of the incident light in a concentrated region around the specular reflection angle. The specular reflection angle equals the angle of the incident light. In this figure, we use the figure which is on the screen. So, we use R to represent the unit vector in the direction of ideal specular reflection, L to represent the unit vector directed towards the point light square, and V as the unit vector pointing to the viewer from the surface position. Angle theta is the viewing angle relative to the specular reflection direction R. For an ideal reflector, I mean perfect mirror, incident light is reflected only in the specular reflection. In this case, we could only see reflected light when vectors R and V coincide with theta is equal to 0. The Phong model, which sets the intensity of a specular reflection proportional to cos ns theta. Angle theta can be assigned values in the ranges 0 to 90 degree, so that cos theta varies from 0 to 1. The value assigned to a specular reflection parameter N0 is determined by the type of surface that we want to display. A very shining surface is modeled with a large value for ns, say 100 or more, and a smaller values down to 1 are used for dull surfaces. So, we use simplified Phong model to obtain by using the halfway vector H between L and V to calculate the range of specular reflections. If we replace V multiplied by R in the Phong model with the dot products N into H, this simply replaces the empirical cos theta calculation with which may be defined as halfway vector is obtained as H is equal to L plus V whole divided by modulus L plus V. So, this simplified Phong model helps us more. Now, the part of the surface which does not visualize, which we termed as shade. So, shading is referred as implementation of illumination model at the pixel point or polygon surfaces of the graphic objects. A fast and simple method for rendering an object with polygon surface is constant intensity shading, also called flat shading. In this method, a single intensity is calculated for each polygon. All points over the surface of polygon are then displayed with the same intensity value. Constant shading can be useful for quickly displaying the general appearance of a curved surface. So, in general, flat shading of polygon facets provides an accurate rendering for an object if all of the following assumptions are valid. The number 1, the object is a polyhedron and is not an approximation of an object with a curved surface. All light sources illuminating the objects are sufficiently far from the surface so that N into L and the attenuation function are constant over the surface, where N is the unit normal to a surface and L is the unit direction vector to the point. Light source from a position on the surface, and the last assumption is that the viewing position is sufficiently should be far from the surface so that V into R is constant over the surface, where V is the unit vector point which is pointing to the viewer from the surface position and R represent unit vector in the direction of ideal specular reflections. So, this is all about our curves, shading and light rendering. I am moving to the IDE. I will show you the assumptions, the algorithms which just I have discussed. With the help of these algorithms, I will use these in the computer programs. So, this is a program to show how Bezier curves are drawn in the computer graphics. In this program, the algorithm, the concept which we have just discussed is being used. So, let us start the program. It is asking for coordinates of Px1. So, x1 coordinate, y1 coordinate, x2 coordinate, y2 coordinate, x3 coordinate, y3 coordinate, x4 coordinate and y4 coordinate. After putting the coordinates, Be attentive on the screen how it is drawn. Here you are seeing that a curve has been drawn. Since the curves are controlled by 2 points with some auxiliary control points, that is why we put here 3 points which are auxiliary x2, y2, x2, x3 and x4, likewise y2, y3 and y4, and this curve is drawn using the Bezier. Students, this is all about the Bezier curves, the shading, the Phong model, etc. Again we will meet in next session. Okay, thank you.